All right, where are we? Okay, so today's class is about network flow. It's going to build on what we did last time. Last time was a long time ago. So let me kind of remind us. The high level question we were interested in last class was, in some sense, trying to understand how well connected two vertices are. And one can quantify this in a number of different ways, but we ended up focusing on two questions in particular that turned out to be closely related. One is, what is the maximum number of edge disjoint paths from S to T? How many different simultaneous connections can you have from S to T? And the other question is, how many edges do I have to delete so that S can no longer reach T? Okay. And these are sort of dual problems where I can think of trying to take paths that sort of pack into the edges. So I'm trying to take a lot of paths, but they sort of use up all the edges that are in the path, and that restrains how many paths I can take. On the flip side, when I'm trying to cut off S from T, that's like saying for every possible way to get from S to T, for every possible path from S to T, I should be removing at least one edge. So that path is disrupted. So in that sense, I'm taking edges to cover all the paths from S to T. So you have this kind of mirror image thing going on. And that actually directly leads to one inequality, which is relatively easy to see. The maximum number of paths you can take from S to T, or you can pack, is always at most the size of any ST cut. Okay? Because an ST cut will have to take at least one edge from each of the paths you pack, and since your path packing is edge disjoint, you'll have to have at least as many edges as paths. So that's relatively easy to see. To try to show they're equal is actually much more subtle, and that's what we spend most of our time discussing. And we focused on kind of the algorithmic part. The most natural algorithm, which was suggested, was just a greedy algorithm for path packing. Let me just take a lot of paths one at a time and see how that goes. Okay, but that might not work. The example we fixated on was this simple one in the bottom right, where if you took that middle path, then you'll conclude I can only take one path from S to T, when obviously you can take two. But it's not a bad idea, because what we eventually did was pretty close, because we sort of focused on this idea of residual graph and residual edges, the idea that I can actually kind of cancel out reverse edges in some way. And so that led to actually a similar, but somehow much more effective algorithm, where every time I take a path from S to T, I'll add the reverse edges back into the graph. And then I'll look for the next path from S to T, knowing that even later on, when I find another path from S to T, if there's some like reversed pair of edges, I can kind of like uncross it as if neither of them had ever been used. So there's this sort of canceling out you can do. It'll become even more clear today. So that was basically the idea. It's still sort of a greedy algorithm. Just one subtle twist though is we add the reverse edges back into the graph. It's a very clever idea. And we're able to show that ultimately, by keeping track of, when the algorithm terminates and we're focusing on this residual graph, the residual graph is where we throw those reverse edges back in. At the end, you're not going to be able to get from S to T anymore. That's when the algorithm stops. So that sort of carves out a set of vertices that S can still reach in a residual graph and everybody else. So that also defines some kind of cut in the original graph. These vertices, and there were some edges leaving it originally. So that defines an ST cut. And we focused on that. And when we retrace the algorithm, we find that every time I take a path going from S to T, I'll use one more edge going this way than going out of the cut than into the cut. So in the simplest case, I'm going from S to T, and the path just leaves the cut. And so it just uses one edge, which gets reversed. So the size of the cut goes down by one. In a slightly more complicated case, maybe the path goes out, then back in, then back out, then back in, but eventually it has to go back out one more time than it goes back in. So maybe there's 5 edges going out of the cut, 4 edges coming back in. And when you reverse all of those, it's still a net decrease of 1. Okay. So what we saw in the proof was that every time I chose a path, the number of edges in the cut goes down by 1 in net total. And at the end, you get down to 0. You pack 100 paths, and your cut goes all the way down to 0, and it was losing 1 at a time. So we conclude that originally that cut also had 100 edges. That was the proof, somewhat quickly. Okay. But the key point, though, is that this algorithm produces some set of paths, disjoint paths, and some cut where the cardinalities were equal. The number of paths that were packed was equal to the number of edges in the ST cut. And consequently, when there's sort of some obvious inequalities, like, of course, whatever the algorithm packs, it packs 10 paths or something, that's at most the true maximum. And however many edges the algorithm finds in the cut, that's at least the true minimum, right? That's just from definition of maximum and minimum. Plus we had our relatively easy inequality in the middle. The number of paths packed is always at most the size of any cut. So we have these easy inequalities, but the algorithm showed that the outer points are equal because it actually gave a path packing and a cut where the sizes were equal. Okay. And suddenly everything is certified to be correct. In other words, if you only had packed the paths, but you didn't have the cut, you wouldn't really know you had the right answer. And simultaneously, if you had some cut, but you didn't have the paths, you wouldn't know you had the minimum size cut. But here the algorithm produces both, and they match each other in size. And that's how we figure out that it's actually an optimum solution. Okay, so you have to kind of study both problems simultaneously. It's similar to the spanning trees. All right. So then we also, out came a bunch of theorems. One is just the graph theoretic fact that the maximum number ST paths is always equal to the minimum ST cuts, regardless of the algorithm that did it. That's an interesting mathematical fact. Then there's the fact that the algorithm produces the maximum number of paths that you can pack and also produces a minimum ST cut. Okay, so there's one graph structural thing, which is surprising in and of itself, plus we have the algorithm to get the job done. Okay, so at the end of the class, I talked a little bit about what we're going to do today. So, the big high-level thing is can we extend the problem from, just unweighted graphs to capacitated graphs? Okay, so this is a little bit misleading because I gave relatively small numbers. The real issue is when you have really, really big numbers. Okay, or even fractional numbers. You have capacity 1.1 or something. And the idea we'll formalize in a moment is that, if this edge has capacity 10, then 10 different paths are allowed to use that edge. So it's not exactly edge disjoint anymore, but it's still sort of packing. Now each edge has some limit as to how many times you can use it. That limit's not necessarily 1. Okay. All right. So what's going on here? Same slide? Okay. All right, so let me first formalize the model a little bit. What does it mean to pack paths with capacities? Especially if the capacities are really big, the total number of paths you pack may be a very large number, right? It'd be exponential in the number of edges just because the capacities are so big. So rather than, thinking of having like a collection of paths all listed out, which might take a lot of space to write down in your computer, we're going to think about weighted combinations of paths. This is pretty simple. I have 10 units of this path, 8 units of that path, and so forth. To sort of set up, another model is going to be introduced later. Let me formalize this. So I can write, for example, PST as the family of all ST paths. Okay, so I'm just thinking of this as like a big collection that contains every possible ST path. This may be exponentially sized, so we won't necessarily write it down anymore. I'm just going to refer to it. Okay. And, okay, so my goal is to sort of take a lot of paths but in a weighted sense. So I want to take, 10 units of this and 5 units of that, so that's 10 plus 5, something like that. Okay. So we're going to maximize. We'll do the objective in a second, but instead of just like taking paths, I'm going to think about it as assigning non-negative values to every path. Okay, and maybe most of them will be 0. Okay, so this is just whatever, some script notation for really saying a weighted combination. I'm mapping the paths to non-negative values. So a unit of 0.2 means 0.2 of that path. Okay. And my goal is to take as much total quantity of path as possible. So that's expressed as, oh, let's sum over all the paths and add up the numbers. Okay. And now I want to obey all the capacity constraints like before. So I'll write subject to, or in short, ST. So for all edges, E. If I sum over all the paths that use that edge, I want that quantity to be at most of capacity. So if I sum over all the paths P, where E is in P, XP, it's at most the capacity of the edge. Okay, so I'm just formalizing what hopefully is a pretty natural model and a natural way to extend edge disjoint paths, which feels very combinatorial, to capacities. Okay. I want to point out one thing, is that this kind of mathematical problem I've described, although it might seem like a graph problem, it also has the quality that like all the math parts are very simple in the sense that, oh, I'm just summing over the x's. And the constraint is a bunch of inequalities. So there's no like squaring anything, or I don't know, take the tangent or whatever. There's no e to the x or whatever, right? It's just addition and inequalities. So this is an example, and we'll see another one later, of what's called a linear program. So a linear program is any of these mathematical problems where you're just maximizing or minimizing like a relatively simple sum subject to linear constraints. It could be equality, it could be less than equal, it could be greater than equal. Here it's just less than equal. And we have linear program solvers out there later. I'll discuss later. One funny feature about this linear program is that you wouldn't be able to write the whole thing down in some sense, because if you wanted to feed it like in a crude way to a computer, you would have to write out every single path from S to T. So this is actually an exponential sized linear program coming out of a small graph or a compact sized graph. So that can happen. All right. Okay, so that's like a weighted path packing, and this allows us to kind of naturally handle capacities and stuff like that. All right, so my goal is, so we're looking at this path packing problem where I'm just trying to pack a lot of paths in total quantity. And my goal is to recover this max path packing min-cut theorem from last time. So I want to argue that, the maximum total quantity of paths I can pack, so the solution to this, whatever the objective value is equal to the minimum capacity of any cut. Okay, so before we're just counting edges in the cut. Now I'm going to add up the capacities of the cut, right? So in that, I guess, simple graph, there's a minimum cut of size 5. Okay, so capacity 5, where I remove one of the 2's and the 3's and a 3. Okay, so I want to show that the minimum capacity of an EST cut is equal to the maximum, quantity of paths I can pack, even in capacitated graphs. And I'm going to start with integer capacities. Okay, so I think I want you guys to try to guess this. How can I try to argue for integer capacities that I have this really nice equality that we got last time. And I want to do it in a slicker way than having to, come up with a whole nother algorithm and go through that relatively elaborate proof. I want to try to reduce to what we did last time. Yeah, okay, so the simplest thing we can do is we can duplicate edges. Okay, so I can take this 3 and I can replace it, with 3 edges. And the 2 was 2 edges, and the 3 was 3, and the 2 was 2. Okay, so nothing simple. I mean, nothing complicated, right? So for integer capacities, we can duplicate edges to reduce to the edge disjoint case. And then you'll just recover that theorem. Okay, so we will duplicate the edges, and then the maximum number of edge disjoint paths is equal to the minimum number of edges in NEST cut. And we can go back to the capacitive graph by, if this path appears, using the same edges 3 times, and then now has value 3 or something, right? So pretty straightforward. Okay, so by duplicating edges, we're able to recover the graph theoretic structural theorem. Now, last time we were able to get a polynomial time algorithm for edge disjoint paths. More specifically, the algorithm's running time was m times lambda, where lambda was the optimum solution, big O of m lambda. And since it's edge disjoint paths, every path uses at least one edge, lambda was always at most m, so this is at most m squared. In some applications, it may be less. But that's not quite a polynomial time algorithm for this integer capacitated setting, but why? Yeah, so if the capacities are big, suddenly, lambda can be like 2 to the n or something, right? And so suddenly m times 2 to the n is not a good running time. So there's some algorithmic issues we'll need to address, and that'll be actually the bulk of the lecture. But we can still take with us some of the structural aspects in terms of just understanding the problem. Okay, so much for integer capacities. How about rational capacities? So this is when the capacities look like, 5/3 or something like that. Okay, yeah, so this is also has the simple trick. So I don't know if these all were weird fractions, right? So, okay, we have all these rational values. What am I going to do? So we can just like clear denominators by multiplying by a big enough number. So I guess, yeah, one can be more careful, but you can multiply 5 times 3 times 9 times 7 times 4. Actually, multiplying one of those 3 is redundant. So you can multiply 5 times 9 times 7 times 4. What is that? 28. 5 times 9 times 7 times 4. 1260? Okay. So we can try to multiply everything by 1260. Excellent. Does anyone want to challenge that? Someone else needs to multiply almost as fast. Okay. Multiply everything by 1260. So, this will be 3 times 1260 divided by 5. 3 times 1260 divided by 2. Yeah. Yeah, okay. So what does a solution even look like with, so by rational capacity, I mean fractions. They can be fractions. Okay, but okay, good question, good question. So, uh, definitely when we're talking about edge disjoint paths, this makes no sense now, right? Because one path uses 1 unit of edge. So one thing that subtly happened in this problem, this linear program, this is a really important point actually, is that I'm not restricting my solution to take whole units of a path. I'm allowed to take half a unit of a path. I'm allowed to take pi units of a path. So all I have to do is assign a real value. So I'm allowed to take 2/3 of a path, in which case I'm using 2/3 of each edge. And yeah, that's right. You can assign any fractional value to that path. So our solution is not going to be integral. It is worth pointing out, so while this problem doesn't require our solution to be integral, in that previous setting of integer capacities, we now know there exists an integral solution. Okay. All right, so rational capacities, you don't have to take integer. Yeah. Okay, so let's look at this. Let's look at the original problem then. So, okay, what's the goal? So my choices, right? Our decisions are in this part. It's saying for every path, I'm going to assign a non-negative value, presumably be zero for almost all of them. So it'll be a sparse solution probably. Okay, and the question had to do with cost. So, okay, this is the constraint. So this limits how much of each path I can take. And up here is the objective. That's the score that I want to win. So the objective is to take as much path as possible, where as much is sort of added up quantitatively. So zero point 0.1 plus 0.3 if I'm taking 0.1 of this and 0.3 of that. Okay, so I want to get a high score, quantitative score. Now look at the constraints. So you asked about costs, but let's read off the constraint. The constraint says for each edge E, if I sum up all the, so I'm fixing on an edge E, right? So I got an edge E, and if I sum up over like all the paths that use E, maybe I'm taking 0.5 of this one and 0.1 of this one or something like that, and E has some capacity, okay? I need to make sure that the sum of those paths using E is at most the capacity of E. So maybe if the capacity of E is equal to like 1, that's okay, because 0.5 plus 0.1 is 0.6, and that's less than 1. If the capacity of E was more like 0.3, okay, now we have a problem, because 0.5 plus 0.1 is 0.6, that's bigger than 0.3. So there's no actual cost in this problem. Other problems have costs. In this problem, we just have capacities. Each path uses, well, 1 unit of path uses 1 unit of capacity. And it scales. So if I use half a unit of a path, it uses half a unit of capacity for each of those edges. And otherwise, it just adds up. Make sense? Okay, good. So this is, I mean, so it's not at all common, we're looking at just one specific problem. It's not at all uncommon to be, I don't know, in whatever real world operations researchy, optimization type of setting and, look at that big word problem and try to write a linear program to model it. Right? So this is a linear program that models, taking paths that fit into the capacities. And each time we do that, has this exercise of how do I interpret the constraints? What are the costs? What are the capacity constraints? Is it covering problems? Stuff like that. So I'm using this problem as an example of linear programs. We probably won't have much time in this class to fully explore it, but it's important to know because it is used quite a bit. Okay. All right, so yeah, we have to keep in mind kind of what we're solving here. It's a little bit different from other problems we've done because of this sort of quantitative aspect, this linear program aspect. Whereas before, edge disjoint paths felt very kind of discrete, black and white, a little easier to think about. Okay. Okay, so for rational capacities, if we multiply by a sufficiently large number, we can clear all the denominators and just turn everything into a really, really big integer capacity. Okay, so we can clear denominators, and that'll make everything integer capacitated. And then we can apply the theorem we just did for integer capacities, which says, oh, the maximum amount of passes you can pack is equal to the minimum capacity of any cut. That's with all the capacities scaled up and big. And then we divide everything back down, but the equalities will be the same because I'll divide both sides by the same number. Okay? So this way I'm again able to recover this maximum edge disjoint pass is equal to minimum, or maximum pass is equal to minimum cut with rational capacities. So we had done integer capacities. I multiply by a big number, so everything's integer capacities. I apply the theorem and bring it back down to the original rational capacities. Yeah. Sorry? Yeah, you're still allowed to do, yes, that's right. That, yes. Well, okay, so the theorem was, okay, so, well, I never fully wrote the theorem, but at this point, okay, let's backtrack. So my question was, or the goal was to reestablish this nice max equals min theorem for integer capacities. And the trick was, oh, I can duplicate edges and think about it as an unweighted graph like last time, and then you get max equals min. Okay. Now I wanted to reestablish max equals min for rational capacities. Oh, and then up here, this is including the fact that you're allowed to take fractional values of paths and stuff. It just turns out it doesn't help you. And so here too, you can do rational, you can do whatever you want. You can do real valued quantities. And right, I want to show max is equal to min for rational values. So we clear denominators, get it to be integers, then max is equal to min, and then I divide it back down and I get max is equal to min for the original capacities. Okay, last but not least, okay, is real capacities. So there may not actually be fractions, there might be something weird like pi thrown in, or square root 2, or something like that, right? Irrational values, they exist. So a simple scaling and clearing denominators trick doesn't work. Okay. But I would love to reestablish, right? Because, these things are funky, right? The question is there anything weird about the numbers that can throw off all this nice theory that we built up last class? So far, the answer has been no. We've been able to handle integer and rational capacities. But now what about real values? Like if I throw in square root 2, is that special? Does that cause any problems? How can I try to handle real values? Sorry? Round it. Okay, okay, take square root, I don't know okay. What is square root 2 roughly? 1.414 or something, right? So if I wrote 1.414, it's not exactly square root 2, but the difference is at most 1 over 1,000 or something, right? Because we went 3 decimal digits deep, assuming that's the right first 3 decimals. Okay, so I know the error is at most. But in general, if I pick any error, if I wanted a 1 over a million error, then I would just have to go, 9 digits deep on the decimal or whatever, right? So in general, I can get arbitrarily small error and get a rational value, right? So I can always get a very good approximation rationally. So I can define new capacities that are rational. Let me do this correctly. So I'll fix some error parameter, which can be arbitrarily small, and we'll make it arbitrarily small at the end. I'll call it epsilon for error, okay? And I'll define, rational capacities, such that this is really, really close for all edges E. Okay, so for every edge of E and E, I'll just get a really, really similar rational value. Okay. Okay, and now what do I know? I know that if I look at like the max number of paths with respect to my rational capacities, it's going to be really similar to the maximum number of paths with respect to my original capacities. Okay, maybe it's going to be like at most m times epsilon. And same thing, the min cut with respect to my rational approximation is also going to be really small. You know, it's adjusting each edge by most epsilon, so the difference will be m times epsilon. Okay. And finally, we already know that for rational values, we have equality. We have the max is equal to min. Okay, so I also know that these two values are equal. Okay. So if we put all this together, it's a little bit dry, so bear with me. You know, we'll get like the maximum number of paths with respect to C minus the min cut with respect to these real values. C is at most, and now we'll do like one of these like triangle inequality looking things. So we'll get this quantity. That didn't work. And we'll also get like this quantity. Right? Something like that. So I can add and subtract the min cut with respect to C tilde and the max path with respect to C tilde because they're equal. Okay. So I'm running out of space, and this will be like at most 2 m epsilon. Okay. Okay. So at a high level, you know, I can use that the rational value for the rational values I have equality exactly. And I can use that to argue that for the real values, I almost have equality. I might be off by something depending on epsilon, right? But finally, the choice of epsilon was arbitrary. I can make it as small as I want. So if I drive epsilon down to 0, that right-hand side goes down to 0, right? The only numbers, so whatever, it has to be some quantity smaller than any number, you end up with 0. Okay. All right, so not a big deal. All we're saying is that by approximating by rational values and then taking the limit, you'll again get max is equal to min for real values as well. So there's nothing special about the numbers. Okay. So I guess the high level takeaway is in many cases, if you're worried about, you know, complicated weighted numbers, if you can just figure out the unweighted case, then often you're just a few like scaling tricks and math tricks away from getting the theorem for all values. Okay. All right. I think that was the driest part of the lecture, and I feel like people are literally crying. So let me just keep going. All right. So the key point is that the duality, this very nice max equals min, still holds in the presence of real values. All that's left to discuss is the algorithmic aspect. Okay. All right. Blank page. All right. Okay. So now the goal is to make some kind of algorithm for maximum path packing and minimum cut with real value capacities. Our last algorithm doesn't work because of its dependency on lambda in particular. So we need to get a better, more clever, strongly polynomial time algorithm. And so to do that, we're going to look at a different model, and I'll connect it to to paths in a moment, called network flow. Okay, but it's actually a little easier to work with when dealing with real capacity. So there's two constraints. I've only shown one at the moment, but the input is the same as before. So you're given some kind of directed graph with positive edge capacities, okay, and S and T. And now we're going to kind of think of that as pipes of a pipe system, okay, where an edge is sort of telling you the capacity of an edge is how much water can go through a pipe, and say on a per second basis. And our goal is going to be to push as much water from S to T as possible. Okay. You could take that analogy and you can think of each water molecule as following a path, and then you'll kind of recover something that looks like a path packing. So, all right, an ST flow. It's a little bit, it's defined, the reason I do this in the second lecture is because it's defined more quantitatively than edge disjoint paths. So my goal is to compute some kind of vector F. It's assigning values to every edge. That value represents sort of how much flow is going through the edge. Okay, so it's a flow vector is a name. Okay. And we have two sets of constraints that are defined mathematically. The first is the capacity. Well, first it has to be non-negative. So we're assigning non-negative flow to every edge. If it's, if you have both directions, you have one different value on top and one different value in the other direction. All right, so it has to be non-negative. And for each edge, if I can only flow 10 units, that's the capacity, then the value of the flow is at most 10. Okay, so the F is always bounded above by the capacity. Now the other constraint has to do with if water is really kind of entering the system at S and being removed at T, and those are the only kind of internal and external sources of water, or inserting and removing, then every other vertex, like in the middle, the water that goes in from other edges has to go out, right? The same amount that goes in has to go out. So that's the other rule called conservation of flow. Okay. So if I'm looking at any vertex other than S and T, on the left, I'm summing over all the edges going into V. Okay, so summing over all UV, and I'm looking at the flow, F of UV. That's how much flow is going into V along the edge, U to V. That needs to be equal to all the flow going out. So that second sum is summing over all the edges leaving V, the amount of flow. Okay. So that's the goal, is to assign sort of this. So this picture is supposed to be relatively correct. So assume like all the edges are unit capacity in this graph. And you can see like, 1 unit of flow up on top splitting into two strands of 0.5 units of flow. And then somewhere in the middle, actually, you have two streams of 0.5 units of flow combining to become 1 unit of flow and stuff like that. Okay, so you can split it up and add it up and, go back and forth as much as you want, but still needs to sort of fit that analogy where what goes into a vertex has to go out as if it were water. And you also have these capacity constraints that say how much water you can send down an edge at any moment of time. Okay, so that's the flow model. It's a little bit funky compared to other problems we've seen because of this very numerical nature of it. This thing where we're assigning values to edges. I don't think we've had a problem quite like that before. Okay. So, right. Now, okay, so because all the intermediate vertices conserve flow, if there's sort of 10 units of flow going into S and out into the system, then how much flow has to come out of T and out of the system? 10. So what goes in has to be what goes out. In the notes I verified this numerically, but it's just adding up the sums. Okay, so as long as you're playing by the rules, what goes in has to be what goes out. And so we can refer to this value as sort of the size of the flow. There's sort of total of 10 units going from S to T. It might be dispersed through all these edges, but this 10 is unambiguous. It's the same that goes out of S and leaves the system, or goes into S and leaves at T. Okay. So that's called the net flow from S to T. And the max flow problem is to find a flow satisfying those constraints with the maximum total size. So I want to send as much flow from S to T as possible. All right. Does that make some sense? It's a bit more abstract than what we did last time, although the connections will become clear in a moment. Okay, so this is another example of a linear program. Right, so look, let's start with our constraints in the second. Right, I'm choosing F. I'm choosing these F values, right? And then there's some rules I have to obey. One was the capacity constraints and also non-negativity. So that's just an inequality, right? F of E needs to be at most C of E. Relatively simple. And the other constraint was conservation of flow. What goes in has to be what goes out. And that's just summing up, 10, 5, 4 needs to be equal to 6, 8, 5. I think that both adds up to 19 or something. Okay, good. All right, so, but the point is, granted the notation is what it is. It's a little dry, but the fact that it's only summations means it's relatively simple. It's boring for us, but it's simple for a computer. That's what matters, right? Computers can add. Okay, and then if I look at the size of the flow, I wrote it sort of pedantically, but it's going over all the edges that leaves S and how much water is leaving it. Plus, maybe for some silly reason, you're also sending flow back into S. So I'm really interested in the net difference. Maybe there's 50 units of flow going out of S, but then other edges are sending 10 units of flow back in. So that's really a net difference of 40. And that's really the size of the flow. So that's all the subtraction is doing, is subtracting out the flow coming back in. You could alternatively delete all the edges going back into S because you shouldn't really be using them. Okay, here's another example of a linear program. Because everything is a linear thing, it's relatively simple. I'll point out that in contrast to last time was that maximum path linear program, which actually had exponentially many variables because you had one variable for every possible path. This one is actually nice and polynomial size. We have one constraint for every edge, we have one constraint for every vertex, and we have one variable for every edge. So this is a nice small m plus n size LP. You could actually write this down and feed it to a computer explicitly. Okay. All right, so this is sort of, I might bring back some discussion about linear program later depending on how the schedule works out. But if I never do, this is almost a canonical example of a linear program that maybe you can, think about if you come across it in your studies. Okay, so, all right, so I defined this sort of funky problem, max flow. And okay, now the question is, let's relate it back quickly to some of these problems we discussed, namely packing paths and minimum ST cut. It seems similar. You're sending stuff from S to T, right? But it's not as discrete as before. Before it's like, 1 unit of path, 1 unit of path, and there's something combinatorial about that. Here it feels like I'm just solving a math problem, right? Even though there is maybe a guiding physical analogy, but it's ultimately a relatively simple to write down math problem. Okay, so is there something here? Maybe not. Okay. How does max flow relate to maximum path packings and minimum cut? All right. Okay, so here's one direction. Okay. Okay, so let's say I have a path packing. Okay. And my goal is to convert it to a flow. Right? So I can define a flow where for each edge E, let's say there's like 10 paths that use that edge E, I'll assign that much flow to that edge. Okay, so let me draw a picture. All right, so let me focus on this edge E. You have S and T, right? And maybe here's one path, and here's another path. Maybe that's 1 unit, that's 2 units. And I'll define a flow where f of E is equal to 3 because I have 3 total paths using E. And I'll do that for every edge. Okay. So now we need to verify that I satisfy my constraints. Okay, so I'm taking my paths and I'm converting it to a flow in sort of the natural way, where for each edge I'm just keeping track of kind of how many paths run through it. Okay, so first the capacity constraints. Why would this obey the capacity constraints? For all the edges. So I start with a feasible path packing, so it's a satisfying solution. Maybe it's a bit abstract. Okay, so so maybe this is what you had in mind. I'll make this quick. All right, so that's not very useful. Okay, so here in this constraint, the path packing said, oh, the amount of paths that use an edge has to be at most a capacity. Right, so that was always true of any path packing solution. And this sum is exactly what we defined the flow on the edge to be. So it's just substituting one for the other, and so the flow will satisfy all the capacity constraints. Okay, so that's fine. What about the what goes in is what goes out constraint? Sorry about that. All right. What about conservation of flow? What goes in is what goes out. Why would my converting path to a flow conserve flow at all the intermediate vertices? Okay, so if I look at a particular vertex V, right, and which has some edges going in, has some edges going out, right? And the amount of flow along any edge is equal to the total number of paths that we're using it, right? So you might have some paths that go like that, and some paths that go like that, and stuff like that, right? And you add all that up and you get the amount of flow on the edge. But since the path starts at S and ends at T, it doesn't end at V or start at V. So it goes into V and it goes out of V, right? So if it adds, +1 to one edge, right, the flow on one edge, it'll also add +1 to an edge leaving the vertex. So the way it's adding up, it's always balancing the equation automatically. All right, so nothing too complicated. But so in this natural way of converting any path packing to a flow, you in particular get a feasible flow, one that satisfies conservation of flow and satisfies the capacity constraints. Okay. Okay, so what does that show you? It shows you that we have a less than equal here. Because for any path packing, I can convert it to a flow that's feasible and has the same size. So the maximum flow value is always at least the maximum path packing. Okay. All right. let's now compare the minimum cut to the max flow. Okay, so previously we showed that the maximum pass is equal to the minimum cut. Now I want to compare the maximum flow to the minimum cut. Okay. If I wanted to argue that the maximum flow is at most the minimum cut, how might I go about it? Well, okay. Let's say I have my vertex S, right? And somewhere out there is the minimum ST cut. Okay, so we have S and we have T. And we have the minimum ST cut. So maybe there's some set of vertices A, and these are the edges leaving the cut. And that's the minimum cut from S to T, removing those edges going across the purple. Okay. Now, and now now we have some kind of flow going from S to T, right? But, every time, like here, the flow is going across the cut, right? It's going from one side of the cut to the other. It's using up some capacity of some edge, right? There must be some edge like that where it's using up some of the capacity. Okay, so if I take all the flow, right, so okay. Okay, so at the end of the day, the size of the flow, right? So I can do the summations, but it's a little bit boring. Okay, so before we had S and we had T, right? And we know that sort of what goes out of S has to be equal to the amount going into T. But in general, if I draw any bubble around S, that leaves out T, right? So imagine there's like a big container around S. So ultimately, water is going to go out of the container into T, right? And there's going to be some net flow out, like maybe some comes back in or something, okay? But ultimately, the net flow out of this bubble around S has to be exactly equal to the amount leaving the system through T, right? So if I kind of capture any number of vertices around S and I measure how much flow is leaving it, how much flow is leaving the bubble, it can only be removed from the system at T. So the amount leaving the bubble will always be equal to the amount leaving T, which is equal to the size of the flow. Because there's nowhere else for the water to go. And I can do the summations to kind of do that slowly, and it's in the notes. But that's ultimately the argument. Okay, so in other words, the size in this case, the size of the flow, the total amount of flow going from S to T, is also equal to the net amount of flow that's leaving the cut. Leaving this set of A around S. That's the bubble. And the amount of flow that can leave the cut is at most the total capacity of the edges in the cut, because those are the edges it uses. Okay? So the size of the flow is at most the capacity of the cut. Maybe you're not using all the edges in the cut, but you're using some of the edges, and it's always bounded above by the edges you're using. Okay, so what we get then is we get this direction. The min cut is at least the max flow. Okay? Because the flow has to use the edges in the cut. Okay. All right, so what did we show? We showed that the maximum path packing is at most a max flow because I can take any path packing and turn it into a flow relatively easily. And I can show that any max flow is at most a minimum cut. That's what we just showed because of this sort of bubble argument. Okay. What else do I know though? I can make this stronger, but how? Okay, they're all equal y? We know that the endpoints of this are equal. So last time we showed that, or in this time too, that max pass is equal to min cut. So everything collapses, right? So as soon as the endpoints are equal, these become equal. And then, okay. So somehow max flow, is it right in between, but also equal? So this problem is actually very strongly related to everything we've been studying. Getting the max flow will get you the maximum path packing value at least. Okay. In fact, the homework problem is going to be taking a max flow and extracting a path packing. So we did the opposite direction just now. We took a path packing, we turned it into a flow. That was relatively easy. The opposite direction is taking a flow and extracting a path packing of the same value. Okay, so we can do both directions, and it's not too bad. Okay, all right, so that's why we're talking about max flow, and everything's equal. And now all that's left is trying to get a strongly polynomial time algorithm for this problem. Okay, so we want to try to get a strongly polynomial time algorithm for max flow that'll also get you max pass with just one more problem left for the homework. And it'll also, as it happens, give us a minimum ST cut. Okay. All right. So, okay, so we're going to try to build on, in fact, we're going to really try to take last time's algorithm and do a little bit better. So we are going to do something like, routing flow along path from S to T. Okay. But first, I think this won't be surprising how we do it, but it's good to redefine residual graphs, but this time in terms of flow. The flow is now just some values on the edges that are at most the capacities. Okay. So I don't know. Here's some example of a graph from S to T, right? And suppose I have 1 unit of flow there in yellow. Okay, so I'm using 1 out of 2 units of capacity. In the first edge, 1 out of 1, 1 out of 2, and so forth. Okay. Now, last time we had to do this elaborate thing was uncrossing paths and stuff like that. With flow, it's a little bit simpler. If I have 1 unit of flow going in this direction, and I kind of wanted to push 1 unit of, let's say there's only a pipe in this direction, and I already have 1 unit of flow going this way. And suppose I wanted to push 1 unit of flow the other direction, right? Well, okay, 1 unit of flow, 1 unit of water flowing this way, 1 unit of water flowing that way would just cancel out to be 0 in both directions. So I can imagine once I'm routing 1 unit of flow this way, adding a pipe of unit 1 in the opposite direction, knowing that sort of running 1 unit of flow this way is really just canceling this guy out. Okay. So our residual edges are going to look more like this after routing 1 unit of flow, where I've added back 1 unit in the opposite direction. Knowing that if I use it in the future, that's really more like undoing flow than anything else. Okay. All right, so just to do a little bit more slowly, more generally, if I have some capacity and some flow, I have some remaining capacity in the forwards direction, and I add capacity in the opposite direction equal to the size of the flow. Okay. All right, so this is from before, but now we want to compute flow. So let me. All right, so suppose we want to compute the maximum ST flow, right? And so this is the exact same algorithm from before that, Ford-Fulkerson one path at a time algorithm. And we're just going to try to adjust it to fit our needs. Okay. So while So remember from before, each time I found a path, I took it and I added the reverse edges. Okay. Now for flow, we'll do something similar. I'll look for a path. Okay. And, now I'm kind of, so if I find a path from S to T, instead of taking the path, what I'm going to do is I'm going to route sort of as much flow as possible along P. Okay, so what does that mean? So uh, if I have some flow, or if I find some path in a residual graph like this, okay, and let's say this is all capacity 1, so I know I could fit 1 unit of flow along this path. So I'll go to my flow vector, and I'll add 1 to every edge along the path. Okay, so now instead of sort of like adding a path, I'm just going to take my vector and update those edge values accordingly. And I'll do as much as I can. So in other words, I'll look at the path and I'll find the smallest capacity of any edge on that path. Maybe it goes like 5, then 3, then 2, then 4 or something. So 2 is my limiting factor, sometimes called the bottleneck edge. And I'll just take 2 units of flow. That's the best I can do along this path. That'll bring that 2 down to 0. Does it, sorry? Yeah, it is greedy. It is greedy. I'm going to ask you guys in a moment. Yeah. Okay. And then the other adjustment we need to make is, we update we don't really add the reverse exactly. We just sort of, we update the residual graph based on how we just did. So I'll equal to the amount of flow, I'll add reverse edges and subtract opacity and stuff like that. Okay. All right, so that what I'm saying is that this is very similar to last time and almost a very natural extension. If I just gave you last time's algorithm and said, oh, extend it to flow, you would probably come up with these ideas. Oh, let's route flow along a path. How much flow? I don't know. Let's just do as much as possible. Right? I think there's nothing too surprising there. Update the residual graph. That definition has changed a little bit based on flow, but it's very natural, I think, given the correspondence between path packings and flow. Okay. I understand it's a little bit more abstract. We have 10 minutes. Okay, that's not good. All right. It's not quite a polynomial. This is going to work if it terminates because it's sort of, but it's not going to be polynomial time. The question is, can you guys think of an example where this algorithm might not be very fast? Yeah. Yeah, well, okay. Well, we are hoping that by routing as much as possible, you do have it, let's say the flow size like 2 to the n. You do hope that maybe you could just, boom, get 2 to the n, or, you're not just going 1 unit at a time. So there is some hope compared to before at dealing with large values of lambda. Still, you're roughly on the right idea. If I just sneak in a bad bottleneck edge, yeah, okay, there's some edges that are huge capacity, and there's some really annoying 1 unit capacity edge that's just killing me because I can only route 1 at a time. So I'm kind of lazy. I keep using roughly the same example. So here there's monstrous edges around the perimeter, right? So the size of the flow is, I guess, 2 to the 100 times 2 plus 1 or something, 2 to the 101. Okay, so it's big. I could have made the 100, 1,000, or a bigger number, right? But if you're not clever about how you choose your path, you're going to route 1 unit of flow like that. And that's going to add back, 1 edge with 1 unit of capacity. And if you're not clever, you're going to run 1 unit of flow. And so each iteration, you only put in 1 at a time, and you have to spend 2 to 100 or whatever iterations to get it to all go through. Okay? Okay. All right. So as things stand, it's not an unreasonable algorithm, but it's not quite polynomial time. We need one tweak. Anyone want to try to guess the tweak? Yeah. Oh, the largest edge leaving it. Is that? That actually will get you, let me just check. That's not a bad idea because it will get you an algorithm and it is actually exercise. Yeah, so this is actually an exercise in the so I'll just give the okay, so the idea is natural. Let's just use the fattest edges along the way. And that will give you a running time that looks something like polynomial in M and log of lambda, assuming integer capacities. Okay, so this is actually not a bad idea. Maybe it's like M squared or something. The polynomial in M is not bad. Where lambda is the maximum value of the flow, is going to be the optimum value at the end. So it would be like 2 to the 100 in this. And it only makes sense for integer capacities. Actually, it can have issues with real capacities. So that's a very natural heuristic that's been studied. I was thinking about putting in the homework, but I haven't decided. Any other ideas? That's a good idea, but not the one that we're going to discuss. Well, something that would have worked on this silly example is if you had always chosen the shortest path from S to T. Like taking that detour in the middle seems silly because it's just longer, right? So that's what we're going to try to explore, is that we are always going to take the shortest path, P, and route as much flow as we can. Okay, so this simple modification is by Edmonds and Karp. Karp is the same Karp from those MP complete reductions. Okay. All right, so that's the only difference. Let me give you the cleaned up algorithm. Is that each iteration I'm going to take the shortest path from S to T and update the residual graph. Okay, another heuristic that maybe you would have come up with if you were just tinkering on your computer. Okay, so good, good. Okay, yeah. This has capacity 1. You can choose either one. So maybe the first iteration you only route 1 unit of flow. The next iteration you route a ton, and then you probably route 1 more unit of flow, and then you're done. So still 3 iterations. Okay. All right, I have to be somewhat efficient because time is running low. Okay. Okay, so here I think is sort of the very interesting part of this analysis. It's very clever because somehow we're going to focus, for some reason, the argument is based on studying the distance from S to various vertices V in the residual graph. Okay, so as the edges, originally maybe V is 5 hops away, and then over the course of the algorithm, we're adding and deleting edges. So how many hops away from S it is may change. The key lemma is that that distance, how many hops from S to V for any vertex V, never goes down. It might stay at 5 for a while and then go up to 6 and 7 and 8. It never goes down. And that's really where it matters that we choose the shortest path. Okay, let me go quickly. So, okay, that's sort of an unusual, first of all, that's sort of a weird thing, right? Because we're now studying distances. I thought we were talking about flow and packing path. What does distance have anything to do with it? So let me first try to explain why this lemma will help us argue that the algorithm is polynomial time, and then I'll try to rush through the proof of the lemma. It's not too hard if I do it right. So I think it's just 2 paragraphs. Okay, so first let's assume this lemma is true. The distance from S to V never goes down as edges get added and deleted from the residual graph. And see why that gives us a polynomial time algorithm. This itself is already very interesting. Okay, so Let's fix a particular edge E from U to V. Okay? And I want to I want to analyze the distances from S to U and the distance from S to V over the course of the algorithm, right? So I'm imagining, there's some like breadth first search layers, and if it's going from U to V, V can only be one layer ahead, for breadth first search kind of thing, right? So each of those purple lines represents one more hop away from S. Okay. So now I want to study this in sort of two possible scenarios. Scenario one is consider any moment when E, this edge, is removed from the residual graph, right? So every once in a while, E might use up all its capacity and get deleted from the residual graph. But if something has capacity 0, we just remove it from the graph. Okay? So if it was removed, that means it was just in the shortest path, right? We must have used it in the shortest path. It must have even been the bottleneck edge, or one of them. It could be tied. So what do we know? E was in the shortest S to T path. So that means we had something like this, right? Where, the shortest path is kind of going one layer at a time. And then it gets to U and it goes to V one layer at a time, right? In particular, V is one layer exactly after U. So whenever I remove E, that means, at least at the beginning of the iteration before I routed that path, the level of V was exactly one more than the level of U. Okay. And here, you could see why it's important that it was the shortest path because of this focus on layers. Okay. Now, what happens when the edge is added back into the residual graph, right? So later, U to V disappeared, but later I might have sent flow in the opposite direction. And that gives capacity back in the U to V direction. Okay, so sometimes the edge reappears, which means the opposite edge had just been in the shortest S to T path. Okay, so that means we had something like this, where you're bouncing up layers and then you get to V, and then U was the next layer, and then you go on to T. Okay, that must have been the case. So we must have that the level of U is now one more than the level of V. Okay, so we have sort of these two scenarios with opposite outcomes. Either level V is one more than level U, or level U is one more than level V. Okay. Now remember, the levels never go down according to that key lemma. Right? The levels never go down. We haven't proven that yet, but the levels never go down. That means, suppose this edge was removed and is reintroduced. What must have happened? Well, at one point in time, V was one step ahead of U when it got deleted, right? And at a later point in time, U was one step ahead of V. Okay? But the levels never go down. So for the only way for me to cross my hands is if this one goes up by at least 2. The only way they can switch order is if they're going up. Okay? Alright, so every time it, deleted, introduced, then they've switched order. Okay? And the only way to switch order is for their levels to go up. And what's the maximum level it can be? Well, it's breadth first search layer, so it's at most like n minus 1. It's n minus 1 or infinity once you can't reach it anymore. Okay? So what does that mean? How many times can an edge get added or deleted? So each time E gets deleted and added back in, one of those levels have gone up by 2. The maximum level is n. So an edge can only get added and deleted n times. Okay? Well, we know that it's in the shortest path from S to T, and levels are the shortest path distance. Oh, well, So maybe I'll be a little more specific. When E was removed from the graph, then E was in particular the shortest path that was chosen by the algorithm. So it's in the one shortest path. And that shortest path requires level V to be equal to level U plus 1 because the shortest path always advances one layer at a time. So the algorithm is only routing along the shortest path. Well, it's global layer, right? One layer is everyone that's one hop away, everyone that's two hops away, everyone that's three hops away, everyone that's four hops away. So if V had like a better layer or something, then that's not the shortest path to V anymore. Yeah. Okay, so there's some kind of subtlety or nuance going on with shortest that barely makes this all work out. Okay, one last observation. I'm sorry about the time. Every iteration removes at least one edge from the residual graph. The question is why? Because I've always routed as much flow as possible. Okay, because we always route as much flow as possible, I'm going to remove some edge from the graph. So I can only remove an edge n times. Every iteration removes some edge. How many iterations can I have? Mn? Well, you meant Mn because there's m different edges, right? And each can get deleted at most n times. Okay. All right. So we only have to run breadth first search to run one of these iterations. Mn iterations and m squared n time. Okay. All right. So that's how the running time comes out. This is the lemma. For every vertex v, I want to argue that the distance from S to V doesn't go down. Okay. And then we'll be done. All right. Okay, so suppose I'm augmenting along the shortest path, P from S to T or something, and I want to argue that no levels go down. We're going to do this by induction on the level of the vertex after the augmentation. There might be other ways to prove it, but for some reason this is how I went about it. Okay, so we'll do it by induction on the level after updating the residual graph, so after routing the flow along P and all that stuff. Okay. All right, so what would be a base case? What's the smallest possible level? Sorry? You can go smaller. The source is the only vertex at level 0, and that'll never change. So, okay, so level 0 is just kind of automatically satisfied. Okay, so all vertices at level 0 afterward, it'll never, okay. Okay. All right, here's a more interesting case. Let's look at some level beta that's bigger than 0. Okay, and let's let V be a vertex where after augmenting, it finds itself at layer beta. Okay. And I'm going to let alpha be the layer before the augmenting. So I want to show that alpha is less than equal to beta. The layer before is less than equal to the layer afterwards. Okay. I've goofed up this proof before, so hopefully I'll survive. All right, so what we're going to do? What we're going to do is we're going to look at the vertex. So, there's some shortest path from S to V that takes beta hops in the residual graph afterwards. So let's let U be that second to last vertex along the path. So there's some path from S that goes to V. That's the shortest path. And I'm going to let U be the vertex that comes right before. Okay. All right, so right. Okay, so we know that level u has to be equal to beta minus 1 exactly after augmenting. Okay? Which means that level u is at most beta minus 1 before augmenting by induction on the level. Okay, so there's our induction hypothesis. U ends up one layer before, and that's already been addressed by induction. Okay. All right, so those are the main ingredients. We have V at level beta, and we have U at level beta minus 1. Okay. And then maybe we can say, suppose by contradiction that alpha is bigger than beta, right? That would be the thing that we claim can't happen. Okay. All right, so what does that mean? That means that level U is like less than alpha, or less than equal to alpha minus 2 before the augmenting. Okay. So we know that alpha is bigger than beta, right? So that means alpha minus 1 is bigger than beta minus 1. So U cannot be in the layer right before in the previous graph. So U might be somewhere else. Maybe U is here or something. Okay. All right. So, okay, so U has to be at least 2 layers before V, before augmenting. Okay. That means this edge from U to V could not have existed in that residual graph, right? Because you can't have edges that jump 2 layers in a breadth first search kind of thing, right? An edge can only go forwards by 1 because that'll be part of the shortest path. Okay, so before, it's a little bit nuanced. Before we updated the residual graph, there was no edge from U to V. Okay? But after updating, apparently there is an edge from U to V, since U was the vertex before V on the shortest S to T path. Okay, so somehow, before there was no edge, after there was an edge, that means that it was introduced. I mean, that means that we must have routed flow in the opposite direction, the previous iteration. Okay. So, sort of running out of space. Okay, that implies that VU was on shortest, whatever path the algorithm took, the shortest ST path before. Right? The only way to introduce UV back into the graph is if in that iteration I used VU and I routed flow along VU. But I'm only routing flow along the shortest path. This also doesn't make any sense because, you know, there's some shortest path to T, right? And what this is saying is that the shortest path is like going to V and then back to U and then all the way over to T. You would never go backwards on the breadth first search layer, right? If U is coming way before V, then V to U wouldn't be an edge on the shortest path because you're just going backwards. And then there's our contradiction. All right, so somehow, I guess what are we doing? We're just very carefully studying what shortest path really means and how edges get introduced back in. It's a little bit subtle, but it gets the job done. Okay. All right, that proves that lemma. And there's our max flow algorithm. All the way through, the algorithm will terminate in m squared n iterations and get you the maximum flow. Okay. On the homework, you'll show how to take this flow and turn it into a bunch of paths if that's what you wanted. All right. Good.